Okay, so let's talk about exponential functions. So this would be a function of the form, this is gonna be a little different. So this is one that you may have mentioned this in Algebra 1 and just had a brief introduction to it, but you haven't done a lot with this yet. You probably won't do a lot with it until really next year. We'll do some stuff with it this year. I'm assuming at the end we'll have some time to do that. But you'll do a lot more next year in pre-calc. So this would be a function like f of x equals some constant. So it could be something like 2, for example, to the x. So what's different here, this is different than a power function. Remember, we kind of left off talking about this. Normally, we're used to having some variable to a constant power, like x squared or x cubed, right? Or eventually, we'll do things like x to the 1/2, that's equivalent to a square root. We'll talk about that later in the year. This time, though, we've reversed that. So we've got a constant base, and the exponent is the variable, right? Now, think real quickly here. What happens? What makes something grow faster? Multiplying it by something or taking it to a power? Power makes it grow faster, doesn't it? Right? For example, if I just multiply something by 3, it makes it 3 times bigger. But if I take something to the power of 3, it's going to multiply it by itself 3 times, right? So, 10 times 3 is only 30, but 10 cubed is 1,000. Yeah, it gets big pretty fast, doesn't it, right? So what's the shape of this graph going to be then? Tell me some characteristics.
It's like a backwards L.
Go ahead.
As x reaches.
Okay, it's going to grow as we get bigger values of x. It's just going to keep growing faster and faster, right? Now, what happens if you take? Let's go the other way a little bit with this. What if x is and this takes us kind of back to some properties of exponents, right? But what if x is negative? Do you remember, and this goes back to Algebra 1, we haven't really talked about this yet this year, but what would happen if I did something like 2 to the negative 1? 2 to the 1 is just 2, isn't it?
Yeah.
That'd be negative 2.
What is a negative, what's it do? Okay, but in this case, we can't really move a decimal in this case. If it were a power of 10, we probably could. But it's a power of 2. What does the negative part of the exponent do? Do you remember?
Just makes it
Well, but how? Like if I did something, let's be more general. Let's not make it a 2. Let's make it an a to the negative m. Okay, where a is just some number and m is some number. How could I write that without using a negative exponent? Do you remember this stuff from Algebra 1 at all?
A times negative
number one
a
makes more
times
Okay,
sense.
I'll show you. It's 1 over, I don't want to use numbers, right? I'll tell you why I don't want to use numbers, because when I use numbers, it's not as powerful, right? In math, and that's part of, I get you want to use numbers because they're concrete, right? Numbers it's easier in a sense to think about a number because you can think about something specific. What's the weakness of using a number though?
It's not as applicable to other.
Okay, yeah, it's not as general, right? If I use a number, I might infer some generalities from that aren't there, right? Like for example, what if I took 1 to any power?
You should infer that.
What's it equal to? Like what's 1 to any positive power? What's 1 to the billion?
One.
Okay, well if I just inferred, I mean I know you wouldn't do this, but I want you to see my point. If I were just to infer some generalities from using, I might think, oh, I take any power to a number and it just gives me back the same number. I got 1 back, right? And so that's why we really don't want to use numbers, because we fall into the trap of being too specific and not general enough, right? It's much more powerful to do things in terms of variables, and these may not even be variables, but they're not pinned down. They can be parameters, right? They're things that we haven't yet chosen the value of these, even if they're constants. We've left that open, right? And then we can always go back after the fact and say, okay, well, what if a were 2? What if a were 10? But let's see if we can see what the patterns are without having to plug any numbers in first. And that's the goal. Like in calculus, we rarely ever use a number. I mean, you don't see them very often, right? At that point, we're so general that it's almost all just variables and constants. Okay, let's close that up. So So here's the relationship I want you to see though, and we'll come back and review this later, in the class, when we get into this in more detail, we'll come back and review this again. But if I have a negative exponent, it just becomes positive on the bottom of the fraction, that's it. And I can switch that around also. If I have something like 1 over a to the negative m, it becomes a to the positive m on the top. So here's an easy way to think about this. A negative exponent is always positive in the other part of the fraction. So a negative exponent in the denominator becomes positive in the numerator. A negative exponent in the numerator becomes positive in the denominator, right? So now let's look at something like 2 to the negative 1. That's the same thing as 1 over 2 to the 1, which is 1/2. Okay, what's 2 to the negative 10? 1 over 2 to the 10th. Well, 2 to the 10th is a big number, right? What is that? 64 would be 2 to the 6, so then we go 2 to the 7th would be 128, 8th would be 256, 955, 12, so it's 1 over 1,024. That's a pretty small fraction, right?
Yeah.
Pretty small fraction. So then if we, now, why do I bring that up? Well, if we're trying to graph the function 2 to the x, I chose a value of x that's equal to negative 10, and I got a really, really small fraction back, right? What about, and 2 to the negative 1 was 1/2.
Yeah.
So we could actually just plot some data points here, couldn't we? Like we'd have, if I go to x equals negative 1, the y value was positive 1/2. What if I pick positive 1? What's 2 to the positive 1? Would be what? 2 to the positive 1 is? What's 2 to the 1? 2, okay? And really, I'm just making a data table, aren't I? Making a t-table. If I pick some values of x and I calculate some values of f of x, if we said if we picked 1, we get 2. If I pick negative 1, I get 1/2. So I can plot over 1 up 2. What if I pick 2? What if x is 2? What's 2 to the 2? 4. Okay, so I could keep going. If I pick 2, I get 4, so I go over 2 and up 4. What about 0? Do you remember that rule? It's another one that you would have talked about a little bit in Algebra 1, but it's been a while. If I take any number to the 0, what's it equal to? 1. Always equals 1. So we could add another little piece to our data table here. If we let x equals 0, we get back 1. So there's our point right there. If I, and you know, if I go back further to the left, I'm just getting smaller and smaller numbers, aren't I? So we can see the trend. This thing's going to look like this. It's going to be very small for large negative values of x, and then it's just going to slowly grow and pick up steam, and then start to grow much faster, right? So that's the shape of our exponential graph, okay? That's the basic shape of any exponential graph. If I were going to graph something like, well, how about if I graph a different function, g of x equals e to the x? I just mentioned this, it's been more than a week ago now. We just mentioned this. What is e? It's a number, it's called the natural number, and it's a number like pi. It's just an irrational number that we use in math, just like we use pi. It's a number, it's 2.7128, goes on forever. It's irrational, okay? I would get a graph that looks very much like this one. The only difference would be, it would just be slightly different in shape. It might, you know, it's going to go through that point. It's always going to go through the point 0, 1, but it might be a little more squared off. It might be a little more of a gradual, but if you're going to look almost exactly the same, right? Depending on what the base is, it's going to impact, you know, what the exact shape of the curve is. But all exponential graphs are going to share some things in common. Okay, let's see if we can find out what those things are. What's the domain of an exponential graph? All reals. Everybody agree?
Yeah.
I could put in any x value and I'm going to get back a y value. So the domain is all reals. Now what's the range?
Y is greater than 0.
Greater than
Okay, greater than 0, right? It's greater than 0 because we have an asymptote over here, don't we? Right, there's that word again. An asymptote is that line we talked about a couple times earlier, right? It's a line that the function approaches but never gets to, right? So here we're going to have an asymptote where?
Y equals 0.
Y equals 0. Everybody see that? We're going to get the x-axis is our asymptote. So we've got an asymptote there at y equals 0. We never quite get to that. So that's telling us that our range is just going to be the values greater than 0. As if we go infinitely far to the left on that graph, we'll get infinitely close to y equals 0, but we never get there. Okay? What about the x-intercept?
There's,
No.
There is no x-intercept, right? None or NA or whatever you want to put there. I think, what does it do on the, I think it does NA, doesn't it? on the- NA, okay, so let's change that. What about the y-intercept?
The y-intercept is 0.
0, 1.
0, 1, every time, no matter what the base is, the y-intercept is always 0, 1. Now, what's the maximum number of roots or zeros?
1.
It's going to be 1 in this case. And for reasons that we'll get to later, it's going to be 1. Now, what about the end behavior? Let's look at the limits. As x approaches infinity, what does f of x approach?
Infinity.
Infinity. As x approaches negative infinity, f of x approaches 0. Whoops. Because of our asymptote, right? Is the function continuous or discontinuous? It is continuous. We would never have to pick our pen off the board to graph this thing, right? Okay? So logarithmic. Logarithmic is, this is another one that we're not going to spend a ton of time talking about this year. Maybe at the very end we'll talk about this a little bit. The function looks like this. F of x equals, now we can do a bunch of different kinds of logs. If I write an log log like that, you're always supposed to include a base to the log. Well, this one includes an indivisible 10. That's what we call a common log. So it's a base 10 log. The more common kind that we use, bad choice of words, we call this a common log. The more useful and typical kind of log that we use a lot of times is a natural log. We write that as, natural log is ln x. Usually it's like a square, ln. Okay, now, all you need to know about log functions at this point, though, is that they are the inverses of exponential functions. And here's the trick about inverses. And we haven't really talked about inverses yet either. We would have talked a little bit about them in Algebra 1. But inverses are going to have, they're going to have reflective symmetry about the line y equals x. Do you remember that? Okay, a little bit from Algebra 1. So if I were to reflect that blue graph over the line y equals x, it would give us the graph of the log function. Okay? And this would be the graph of the log function, the base 2 log of x, because we have a base 2 here, right? So what's the look going to be then? Well, instead of going through the point 0, 1, what point is it going to go through?
0, -1.
No. If I'm reflecting it over this line,
1, -1.
1,
Negative.
no, 1, 0. Yeah, it's going to go through the point 1, 0. Okay, and there's another way to think about that, and you're going to go, aha, when we talk about inverses later. Because the way that you calculate an inverse is you just switch x and y. You exchange the x and y values and you solve for the new y. So the whole point of inverses is you're exchanging the domain and the range. Right? So if this point has coordinates up here, if it has coordinates 0, 1, then when we switch the x and the y, we're going to get the point 1, 0. Right? So that's the corresponding point on the inverse graph. And then instead of the asymptote being the y-axis, it's going to be the x-axis, right? And isn't it just going to look like this? I need to move that's not a very good spot. It's just gonna go like this. I'll draw this a little better. Even better. This pen is just not quite calibrated. So it looks like that. That's the basic one. So what are the characteristics of this one? Oops. So this one starts off, instead of starting off increasing very, very slowly and gradually increasing more rapidly, this one starts off increasing very rapidly and loses steam. As you go further to the right, it gets flatter and flatter. And the rate at which it's climbing decreases as you move to the right. Okay? So what's the domain of this function?
Domain is greater than.
Okay, x is
Less.
greater than 0. Now I want to, this is going to be kind of an aha moment for you a little bit. What did we just say about inverses? We'll come back and talk a lot more about this, but all we do to find an inverse is we exchange the domain and the range, right?
Yeah.
Well, what was the range up here?
Greater than
Y is
0.
greater than 0, so that means the domain here must be x is greater than 0, right? What do you think the range is going to be if the domain of the exponential function was all reals? What's the range of the log function going to be? Because they're inverses. All reals. Okay. What's the x-intercept?
1, 0.
What's the y-intercept?
And
Right? Because we're just flipping those, right? What's the maximum number of roots or zeros on this one?
1.
It's 1. End behavior, as x approaches negative infinity, well, really, can we even approach negative infinity on this one? We really can't, can we? So there's maybe a better thing that we could do on this one. We could do something like we could approach, well, let's do positive infinity first. As we approach positive infinity, as x approaches positive infinity, what does f of x or y approach? What do you think? Infinity, right? It's going to grow slowly, but it's going to grow forever. So that one's infinity. But what about this one? We can't go to negative infinity. What's the smallest value of x that we could approach? 0. Okay. We could approach 0. As x approaches 0, what would f of x approach? Aha. There we go. Right. Make sense? And in this case, the asymptote is going to be what?
X equals 0.
Is going to be x equals 0. Okay, continuous or discontinuous?
Continuous.
There you go, continuous. Okay,
What does
good.
that even mean? What is the point of stating if it's continuous or discontinuous?
Okay, well, there is a point. Continuous means a function is continuous everywhere if I can draw the entire function without ever picking my pen off the board. So I think we only had maybe one example of a function that was not continuous, and that was the reciprocal function. I had to pick my pen off the board to draw both parts of it, right? Okay, makes sense? So why do we do this? Here's just a relatively short list of functions that we know what they look like. We know what the parent graph looks like. Why are we doing this? Because now the next step is we want to learn how to transform any parent function in a very predictable way, right? So we're going to focus on the easiest one to do, which is the absolute value function. Okay? So what I want you to do now, we're going to work towards filling all this stuff in. But what I'd really like you to do now is on Moodle, I just built some stuff today for you to kind of play with. So here it is. You're going to go into Unit 3 in Moodle, and if you click on the Interactive Transformation Fun,
Right.
it's going to take you here. Okay, he's having fun.
That's what I look like when I have.
It is. That's what you look like when you do math. So it takes you here, and then if you click on each of these, we're gonna explore one at a time. I'll let you guys do this. You can work in little groups if you want to. You're going to go through this, and you're going to try to just remind yourselves how all of these transformations work. And it should be pretty quick. And then we'll come back together and we'll summarize. So like if I click on this first one, for example, so it's going to take you here. This is a graph of the P for parent graph. So parent graph equals the absolute value of x. Okay. Alter the value of k and observe how the graph changes. So just on this one, you're just going to drag this little, you can go in and type in manual values, but it's probably easier just to do this, right? I'm just gonna drag this little slider and choose different values of K, and then see what it's doing to the red graph, right? The red graph is gonna be the altered graph, and the green graph is the parent graph. Okay, so do that for each of those. There's like 5, I think. 5 little
Just to be clear.
Desmos documents that you can go in and play with a little bit,
So
okay?
A is slope, H is.
Well, you'll
Y.
figure it out. I want you guys to kind of just go in and figure it out. You can work on one computer, you can work with a partner, I don't care. But have at it.
But
Okay, so if I go into the transformations then, you tell me real quick. Can I get your attention, please? Oh, I gotta log in. Hang on. Here we go. I'll just do this.
Which says.
All right, so if I've got something of the form right here, if I've got a parent graph, it could be anything, right? In this case, it's an absolute value function. Everybody's focused up here. And I've got a transformed function that's of the form a times whatever the function is of x minus h plus k. The goal is I want you to be able to articulate to me what happens when I subtract h from x inside the function, what happens when I add k outside of the function, and when I multiply by a, if I multiply the original parent function by a. So what's the effect of subtracting h from x? So right now, the values of a are 1, so it's doing nothing. Multiplying by 1 does nothing. H is 0, so I'm subtracting nothing, and k is 0, so I'm adding nothing. And so the transformed graph, the red graph, overlaps exactly with the parent graph, because I haven't done a transformation yet, right? What's going to happen if I plug in a value of h equals 3?
It's gonna move 3 to the right.
It's going to move 3 to the right or the left?
Right.
To the right. That's correct. So the value, and this is one that gets a little confusing. Can I get all earbuds like away? I just don't like those even remotely close to your ears during class, if that's all right. So if I pick a value of h equals 3, look what it's doing. The value I'm subtracting from x is how much I'm actually shifting, translating the graph horizontally to the right in the positive direction. Okay. When are we out of here? 18. Okay, so we'll talk more about that tomorrow. About why we'll try to kind of figure out why it works that way. What about k? If k is positive 1, what's that doing?
it's gonna move it upward.
It's going to move it up by 1. So the number that's being added outside of the function is the vertical offset. That's how far we're translating vertically, correct?
Yeah.
What
And
if
it's
a
not.
is 2?
It's gonna be.
It's gonna be a
linear.
different
It's
slope.
Okay, in fact, what it's doing is it's going to be stretching everything, stretching the function by a factor of 2. And here's how I want you to see that. So normally, when I go 1 to the right from the vertex, I would only move up by 1 on a regular parent graph, right? But in this case, if I move 1 to the right, I'm now moving up by a factor of twice that much. So I've stretched the graph by a factor of 2. Did everybody see that?
Yeah.
If I made a equal to 1/2, then instead of going over 2 and up 2, I'm going to go over 2 and only up 1. Everybody see that? If a becomes negative, what does it do?
It goes down.
It's just, all it's going to do now is it's going to reflect the graph vertically. Okay, we'll pick this up tomorrow, but that ought to get you going on the assignment.
What are we doing on Friday?